Yeah, a little bit of background before we jump in. So I think as Derek mentioned earlier in this presentation, we've been using Model Predictive Control for our low-level controller since the beginning of year 3, I think. So about 2 years now. The initial iterations were developed as Mohammed Dayoud was completing his thesis. And he did actually a presentation about that don't remember how long ago it was at this point, but so could have been 2 months, could have been 6 months. But this is a newer iteration on that. The initial conception was for a optimal control course that I was taking last term in SIDE. Really great course, would recommend it. And then I took it back to the WATonomous team and we did some like real world implementation improvements to get it to work with our stack. So I'll go over those as well. But yeah, without further ado, let's jump in. So the idea is that we want to achieve both local planning, meaning how to react to like simple stimulus in the environment. We're not talking about complicated stimulus like traffic rules, but restricting our scope just to anonymous static entities that might show up on our route. So that's what we mean by local control is reacting, local planning is reacting to those entities. And we also want to simultaneously control the vehicle. So have a model of how the how the vehicle is going to react to the commands that we send it and be able to send commands that achieve some local plan. Yeah, so the overall problem description is that the simultaneous local planner and controller is given a high definition lane map, like the one you see on the right. We're given a reference route through that lane map, which is just simply the center of the lanes, the center of some lanes from the HD map, shown in pink on the right. A reference velocity that we want to maintain, and a description of free space. And the description of free space, of course, warrants a much deeper discussion of how that's formulated and described to the controller, and we'll dive into that. And then the objective of this control algorithm is to move the vehicle along the route, which is in pink, only to move in free space, which again we'll discuss later, and also to do this driving task in a comfortable and efficient manner. So not violating any body metric constraints that would be uncomfortable for the passenger, and also maintaining as close as possible to the reference velocity. Any questions about the problem setup? Nope. Yeah, so let's move on into how we formulated. So there's potentially many different combinations of controllers and higher level planners that could be used to conquer this problem. We're going to take a optimal control approach. So one of the first steps in that is to formulate this problem into a optimal control problem. So the model of our system that we're going to be assuming to formulate the OCP is as follows. So we're going to assume that we have control over the longitudinal acceleration that we can impart onto the vehicle. We can change that acceleration instantaneously within some constraints, which I'll go over next. We can also control directly the road wheel angle of the vehicle. And the last thing we have control over is a new variable that we introduced for this task, that Mohammed Dayoud originally introduced for the path following task, which is the path virtual input. So this is a fraction of the route that we want to complete at some sample time. So for example, let's say that the route is parameterized so that 0 along the route is the beginning of the route, and 1 is the is your state when you have completed the route. This control variable that we're deciding on dictates how far along that parameterized route we want to move in a certain control cycle. All right, so yeah, those are the 3 variables that we want to decide on. And then state variables that we affect, given those control inputs, include the inertial or static frame pose, so position and orientation, along with body frame metrics, including longitudinal, lateral, and forward direction velocities. And we also maintain the path parameter, which is the vehicle's current fraction along the route. So you can think of it as the accumulation or the integral of the path virtual command. Okay, and lastly, we have the measurements that come back to our control algorithm to complete the feedback loop. And we assume these are coming from a inertial measurement unit, like the one we have on the Bolt platform. And these measure with some degree of noise the inertial frame pose, the longitudinal and lateral velocities, and also the longitudinal acceleration. For the predictive model that we'll use in the model predictive control strategy, we use a nonlinear kinematic bicycle model. So let me just skip on to the next slide to describe in a little bit more detail. So on the left, we have the schematic of the kinematics, and on the right, we have the related equations. So the thing to point out here is that all of these equations are based simply on the kinematics of the single track model. We're not currently including any tire force modeling. So the important thing to note here is the dynamics of our yaw. So this is the state yaw, and its dynamics are dictated by the steering angle that we apply, and also the what's called the kinematic slip angle, which is the difference between the heading of the single track and the direction of travel of the vehicle. And that's estimated using this equation here. So this this prediction model is used in our objective function to penalize certain behaviors of the vehicle. So specifically, what we want to penalize in this model predictive controller is, of course, the error between our state and the reference trajectory that we're trying to follow, which is just coming from the center of the lane. We also want to penalize the velocity error with respect to the reference that we're given. We want to penalize the path parameter, this one here, which you can think about it as the distance to route completion. So we always want to encourage the path parameter to tend towards 1 so that the vehicle proceeds along the route. And then this is a novel introduction here, which is penalizing the lateral jerk, or the change in acceleration between any two states along the prediction horizon. Yeah, so one other thing to note about the objective function and the weights that we apply to these terms, they are adaptively changed based on the distance to the nearest obstacle. So for example, if we're in the obstacle avoidance condition, if we've switched into that condition based on our distance to a obstacle, then we assign a lower penalty to our reference pose error. And this allows us to deviate from the reference in order to avoid that obstacle. Whereas if we only had one weight setting, the controller wouldn't have the flexibility to make that maneuver. It would probably just stop, because it would value maintaining the reference would have a lot larger value than like proceeding along the route, which is encouraged by the path parameter. Then lastly, talking about constraints, which is one of the main advantages of a model predictive control scheme, since at the end of the day, it's solving a optimization program, either a quadratic program, or as we'll see next, a nonlinear program. It's easy to incorporate states both on the control variables and the state variables. So for example, we want to obey SAE's guidelines for the auto drive challenge that they published regarding body frame metrics for passenger comfort. So this bounds longitudinal and lateral acceleration, as well as longitudinal jerk. And also, very importantly, was the initial objective of only traveling through free space. That's also formulated as a constraint. So here's the entire more formal table of optimal control problem constraints. But yeah, so we have some these non-holonomic constraints just describe like the physical bounds of the vehicle. So for example, the dynamics equation that we're assuming that the vehicle behaves like a single track kinematic model. So we have a constraint that like the next state vector of the vehicle is a discrete application of that dynamics model. So this forces our control algorithm to obey the non-holonomic constraints that we're enforcing on the vehicle. There's also other non-holonomic constraints, such as the range of the wheel shaft of the vehicle. There were legal constraints about the maximum speed, the comfort constraints imposed by the SAE guidelines, and then feasibility constraints, only having the vehicle only occupy non-occupied regions of the environment, so we don't have a collision. And also, we don't want the vehicle to proceed before the route or exceed over the route. So this limits the range of the, what did I call that? The path parameter state.
Yeah, sorry, Rowan, do you want to define what a holonomic and non-holonomic constraint is?
So a non-holonomic robot is one that has restrictions on its degrees of freedom. So a completely holonomic robot, whatever like dimensionality it occupies. So let's say it's placed on a line. a holonomic robot operating in the space of a line could like travel back and forth on the line arbitrarily, right? But if you impose some non-holonomic constraints on the state of this like particle robot traveling along the line, perhaps you say that it couldn't arbitrarily change its acceleration. That would be putting a non-holonomic constraint on that like line traversing robot. So for our model, we have some more complex non-holonomic constraints. So we assume that our space that we can move around in is the 2D plane. But we can't just arbitrarily move from side to side, forwards or backwards. We have a pretty complex interaction of how our position changes relative to the other entries of our state vector. But yeah, like overall, this model here is just describing how the states interact to produce the non-holonomic behavior of our vehicle.
Gotcha.
So this could be an interesting design consideration for that helicopter landing pad doohickey, because you might, initially imagine that as a holonomic system, which would mean, if I'm right here, that it could move in any direction whenever it felt like it, try to match up to the helicopter. But is that a correct understanding?
So you're talking about the platform that moves around on the deck. Yeah. So it depends on, I guess, the mechanics of it, but like in the real world, it's very unlikely to have a holonomic system. Most mechanical, you need to have an extremely flexible mechanical system to arrive at that. Most real world mechanical systems that I've run into have non-holonomic constraints. Like for example, if the platform was moving longitudinally on the ship deck, the mechanics might not be set up to also allow it to rotate when it's moving longitudinally. So that would be another non-holonomic behavior.
Yeah, so like any constraint stemming from like the wheel action, like how the wheels move, you cannot perform like any arbitrary move. That would be the constraint.
Yeah. Yeah, so we can definitely spend some more time on this slide. I know presenting the optimal control problem is most of the design of the controller. So if there's any other questions about this design, yeah, we can definitely spend a few more minutes on it.
Sorry, Rowan, for those of us who are not very familiar with control problems in general, can you define how optimal control is, different than a generic control problem?
Yeah, so this would be a great question for my professor last term, but I'll give my best shot on summing it up. So yeah, how it was presented in the course was like all of the mathematics behind it was presented through the lens of a branch of calculus called the calculus of variations. So like what this all boils down to is a optimization problem, but it's not the optimization problems that most people here are probably familiar with, which is given a function description, you decide on the constant inputs to that function. That would be the optimal point. You'd also need to check convexity or concavity, but it would be some local optimum point, which is like constant. However, when we shift over to more complex questions of optimality, for example, what is the optimal sequence of control actions? That's no longer just a single function that we want to optimize. We're actually optimizing over a space of functions. So for and this arises because we are like the input to our objective function is a function that produces control inputs. That makes sense. So we have a function, which is our control algorithm, that produces these like decision variables. But how we want to optimize that control function is with respect to like a higher level objective function. So what we're actually optimizing is this objective function, but like instead of shifting a point around into like, okay, if I shift the point a little bit to this side, does the function increase in its value or decrease? We're actually introducing variations to the underlying control function. So we're like, if we change the parameterization of this control function a little bit, does our overall objective function increase in value or decrease in value? So yeah, that concept of calculus of variation, you can phrase a large family of control problems inside of that by trying to optimize the control function given some higher level objective function.
I see. Okay, so is it correct that I understand optimal control problems are more like they almost feel like a certain subset of like regular optimization problems, because like you said before, for regular optimization, we're given like some explicit cost function of that problem we're trying to solve, and with all the independent controls variables that we have control over, you can change them in any way, just like a totally holonomic system. However, these type of optimal control problems are kind of like you cannot just change those variables in any way imaginable, only through a set of like these system models. So these functions control how you can change the variables, and the study of optimal control is the optimization of problems of this kind. Is that kind of correct?
Yes, although I wouldn't, like you initially said it was, you could think about it as a specific kind of optimization, but I would say it's kind of the opposite, where the calculus of variations is more general than the calculus of single functions, because it incorporates not only single functions, but also variations to single functions. So like if you added a small change in the function, how would that affect the overall cost index?
I see, because you said that this is a whole set of functions instead of just one, right? Okay, so it's an extension in that sense.
Yeah, exactly. We're optimizing over every single function that could exist, instead of just optimizing over the parameters for one specific function.
So if you don't mind, I might have like a firm example, and you can tell me like if I'm thinking about it wrong. Like this is how I kind of think of it. If someone gave you like a fixed path, right? that you want to drive on, and said like, how should you, like what speed should you travel along this path, such that, you know, your lateral jerk was minimized, you would find a particular like set of velocities, right? But now someone's asking you, well, now find me, not like, I'm not going to give you a fixed path, but I'm going to give you a set of paths, right? So say they gave you 100 paths, and they said, find the path that required the least time to get to your objective, but then also find the velocity that you need to travel along that path. So now you are solving two kind of optimization problems.
I see.
And that I think might give you more about, yeah.
All right, very cool. Thanks.
Yeah, no problem. Yeah, and I feel like my description of the calculus of variations, it's hard to actually get a mental model for it without some graphics of how it compares to just the calculus of functions. So yeah, I can post a few slides from the presentation that I learned about it from.
Hey, all right.
All right. Yeah, any other questions about the optimal control problem?
Actually, yeah, Rowan, if you don't mind me asking again, now that we, I kind of get a picture of what these kind of problems are, how would you summarize the general framework we use to solve them? Because I know that it's obviously a very complex, this framework will be very complex, but is there like some sort of quick overview that you can give us?
So there, I mean, in the course I took last term, there was a few algorithms that were proposed. Like you can, in some cases, you can directly solve these calculus of variation problems to obtain the optimal control variables. And so if you look up like Euler-Lagrange equations, those are some of the, like, at this point, very, very old, but tried and true methods to solve calculus of variation problems. And those equations can be used to derive like control algorithms that are still used today, such as LQR, linear quadratic regulators. That was one of them that we derived. And I'm sure there's many others. And then on the other side of it, model predictive control is another big branch where you transform. So it's not applying calculus of variation directly. Instead, it is transforming the optimal control problem back into a optimization problem. It's basically saying there's no analytic way to solve this calculus of variation problem. Let's transform it back into a optimization problem and then plug it into a optimization program, so solver. And yeah, I mean, I can also give you the slide deck on how that transformation is done. But basically, it boils down to applying a sampling frequency to the prediction model and using the non-holonomic constraints. Kind of, yeah, just like summing up all of the costs that are incurred throughout the entire prediction horizon, and then trying to minimize that. So it's kind of like sampling the space of possible functions multiple times, and then just trying to optimize the parameters of like that set of functions that you sampled.
I see. Yeah, this transformation sounds like where all the magic happens.
Yeah, and it's actually really, really simple. I mean, you can think about
Oh.
it in complex theoretical ways, but to implement it, I mean, it's kind of like the more intuitive way to solve a optimal control problem if you didn't know about the like the direct methods for solving calculus of variations.
I don't know, I'm pretty sure when I learned it kind of seemed like magic.
Oh. Oh,
Well, I will post a slideshow. Yeah.
very interesting. Yeah, so like after all this magic stuff, yeah, then you can plug into other existing frameworks to solve this this transformed optimization problem.
Yep, exactly. And that's what I'm going to talk about next.
Oh yes, please go ahead.
unless anyone else has questions about the formulation. Okay. So yeah, so how do we want to solve this optimal control problem? I know that we've kind of peeked ahead and talked about this, but hypothetically, this optimal control problem could be solved using a variety of techniques. So we have many constraints because we're trying to solve, or we're trying to encode a pretty complex driving behavior into this controller. We also have a nonlinear system dynamics coming from these kinematic equations. In some literature, these trigonometries are simplified. They're either linearized multiple times at different operating points, or they're just completely ignored because we assume that we have a very small steering angle, perhaps. But this isn't the case for us. We're going to have large steering angles, potentially, because we're doing very sharp turns at times. Yeah, so because we have these nonlinear system dynamics, we chose nonlinear MPC. So this was the same solution technique applied by the original Mohammed Daoud version of the MPC. So in order to transform these dynamics into a optimization problem, you can discretize them using the Runge-Kutta family of approximators. So this allows you to more accurately sample these dynamics equations without having to solve these ODEs. Allows you to accurately approximate how this dynamic system would evolve over time. And then the technique referred to as multiple shooting enforces this non-holonomic constraint in the implementation of the nonlinear program. So I can definitely show you guys the actual Python code that applies this RK4 technique and formulates the result as a constraint, and that overall is called multiple shooting. Then after that, the OCP has been transformed into a NLP, a nonlinear program, which then is plugged into some optimization implementation. We use the interior point optimizer, which is a library which has a interface through the Casati software package. And yeah, this easily integrates into our ROS node because it has a Python implementation. All right. So yeah, for those of you that this went over the head of, I can definitely just link you the 20 lines of Python code that actually apply the RK4 and set up the constraints. I think that'll make more sense. But any questions for now? Yep.
Any reason for using RK4?
So this was the code that we inherited from Mohammed Daoud to use RK4, but I think generally their approximation scheme is pretty widely accepted as a good trade-off between like algebraic complexity of how many samples they take of the dynamics, good trade-off between that and the like practical accuracy of the resulting approximation. But yeah, if there's any other differential equation approximation schemes that people know of, we could certainly try those out as well.
Sounds good.
Okay, so yeah, these were the preliminary results from Carla, which we all know and love. So this was with just hard-coded obstacles that the controller knows about. They're not being observed by the LiDAR or anything. But yeah, it's able to perform a pretty smooth double lane change and also make a turn. But I just wanted to mention a few kind of practical considerations and implementation details that we ran into when we applied it at Westurk. So yeah, so for the implementation of the only occupying free space constraint, we broke these down into obeying the road surface boundaries and also maintaining a safe distance to obstacles. So for road surface boundaries, these were enforced via maximum lateral deviations from the route. You can think of at each point along the route, there's a maximal distance that the car can be to the left or the right of the center of the lane before going off the road. And the behavioral planner, which has the high definition map, knows what these maximum deviations are. So yeah, these are instructed by the behavioral planner and then are transformed into constraints on the controller, which prevents us from moving off the road while we do our obstacle avoidance maneuvers. And the other free space regions we need to care about is maintaining a safe distance to obstacles. So currently obstacles are represented just by points in space, which are obtained by the occupancy grid. And then we aggregate all of these points by just taking a minimum function over all of them, like pairwise. And then this final minimum function is constrained as well. However, if you have a minimum function that includes like hundreds of points, the Casati optimization library starts to fail to find solutions. So we had to filter the occupancy grid down to a small number of obstacle points that we care about, specifically the ones on the road surface, before we transformed them into this minimization constraint. And then finally, one other practical concern was how do we stop at the end of the reference? We played around with a few ways to try to change the optimization problem to enforce this. Nothing really worked, so we ended up just going with a heuristic measure of applying, sorry, not maximal acceleration, maximal deceleration once we're within stopping distance to the end of the reference. So stopping distance is defined as the distance that we need to change our velocity to 0, while also obeying the jerk and acceleration maximums as imposed by the SAE guidelines. So depending on how fast we are moving, you can basically always monitor your stopping distance. So like how much runway we would need to in order to stop while maintaining these guidelines. And then once we arrive at that distance from the end of the reference, then we apply maximal deceleration. Yeah. Okay. Any questions about these implementation details?
Did you have any issues with the maximal deceleration stopping? I remember they tried that in, like Mohammed tried that in year 3 and it didn't work terribly well.
So what we changed is that we still allowed the optimizer to control the steering angle, even when we're within this stopping distance window. In Mohammed's implementation, it was both maximal deceleration and also the steering angle was just hard-coded to 0 once we got within this stopping distance window. So if you didn't have like the exactly correct heading, then you would occur like a pretty large error on the tracking of the reference. But yeah, still allowing the optimizer to solve for the steering angle while applying this deceleration give us pretty accurate stopping.
Nice.
Alrighty, so I'm sure you guys have seen this and are kind of bored of it at this point, but yeah, some experimental results from when we applied the controller at West Turk. Here's from the year 4 demo, it taking a pretty sharp turn. And then on the right here, we were having a fair share of trouble getting the obstacle avoidance to work reliably. So we see, sorry, let me just replay this and do it a bit slower. So we see that as we approach the obstacle, our computation time spikes to about solving the optimization problem only once every second, which is not viable. So you see that the solution is lagging a little bit behind the vehicle as we approach. And then eventually we do find a solution that takes us to the left to avoid the obstacle. But then at this point, the solution and the actual pose of the vehicle are diverging a little bit. And then this only gets worse. Like the solution proposed by the optimizer and the actual orientation of the vehicle disagree a lot. And then this only gets worse as the vehicle continues to the side of the road, but the optimizer, for some reason, thinks that we're just going to continue back onto the reference. So yeah, definitely still a fair share of failure cases in the controller that we're currently working on as we try to work towards a publication in this area for the team.
Do we know what happened back there when the optimizer asks the vehicle to go backwards?
Yeah, let me bring up that slide again. Yeah, so to me, it looks like this is a programming bug where, in order to make sure that there's alignment between the optimization problem that's being solved and the actual state of the vehicle, we add a constraint that the initial state of the optimization has to be like exactly matching the measured state of the vehicle. But clearly the first state in the optimizer is not matching the measurement of the vehicle by the IMU. So I think there's some just bugs that we have to figure out on the initial conditions that we're passing into the optimizer to figure out why something like this can arise.
True. Also seems that a few ticks before we ran into this problem, the optimizer, as you said, the optimizer started lagging, but the circle on the top left is still green. Does that mean it's lagging, but we're not detecting that it's lagging?
So this is just the wall time computation of the Casati solver. And yeah, we definitely want it to be less than like 25% of this entire circle. So it looks like it had that big spike at the beginning, but then as we're generating these initial solutions here, it seems to all be fine. But yeah, I just don't know why we have this disagreement between the solution and where the measurement of the vehicle actually is.
Right. Cool. It's something that we need to look at.
Mm-hmm.
Also, to speed this controller up, would it be feasible to perform a linearization at each step? At Waterloo, we linearize the vehicle with some parameters for the model, and and we use a linear MPC to solve the, actually it's called adaptive MPC, where we change the model every single tick based on the current speed. Maybe we can do something similar here, where we offload the work to the linearization step before the controller.
Yeah, absolutely. Yeah, we can talk more about that. I guess the trade-off boils down to the computation time for the linearization, like how many times you have to, how often you have to do that, and then versus how fast the quadratic program versus the nonlinear program can be solved. And like the quadratic program is just matrix optimizations, right? So I'm guessing very fast.
Oh, here we're solving a nonlinear. I mean, is here quadratic? I had the assumption that it's not even quadratic, the kinematic bicycle model.
Sorry, if you linearize the model, then like you could put it into a quadratic program solver.
Oh, I see. Makes sense. Cool. Oh, also another question regarding this. I remember a few terms ago, we were having this discussion of how do you fit the reference of the MPC onto a discrete set of points generated by the path planner. Did we end up doing that?
Yes. So we take a window around the vehicle, like 10 meters back and 10 meters, sorry, like 30 meters forward on our route. And then we split, we like take all of these points, sample that like, I forget the exact resolution, but so that there's like 50 to 100 fit points for the function generator. And then the fit function that we use, the same as Mohammed, was a quintic spline. So that's the blue overlay.
Oh, cool. That makes sense. Oh,
Yeah,
sorry.
you see that as there's like a more complicated topology of the yellow line here. Sometimes the quintic spline doesn't fit that well. You need to have a pretty small local window. Like if the window continued all the way down here, then this blue like quintic spline line would be totally crazy trying to minimize its squared error. But using this like pretty small window, it works well enough for the spline fit.
Do we adjust the window size based on the curvature of the road? Or is the window size always small enough?
Yeah, we have it small enough so it seems to work for all of the conditions at Westerk. But yeah, doing it dynamically, like doing a lot of stuff dynamically based on curvature would probably be a good idea in general, yes.
Cool.
All right, so yeah, just a few concluding remarks here in future work. So overall, we found that bringing the free space description into the OCP formulation yielded promising results for simplifying the entire WATonomous motion planning pipeline. But there are some notable implementation limitations that I mentioned. So there's a limit on the density of obstacles in the scene. If there's hundreds of points on the occupancy grid that we care about, the Casati solver will start to fail. Also, the weight tunings, of which there are many, especially because we have different settings for obstacle avoidance versus just nominal tracking. These tunings are pretty arbitrary, meaning they were decided upon by myself and other members during our manual tuning at Westerk, but they could certainly fail in other scenarios that we didn't tune them on, and they're basically highly sensitive to which scenario the vehicle is driving in. And then lastly, as I brought up earlier, the kinematic equations are only valid for like operational regions where the tire slip, sorry, not split. I was working on this pretty quickly. Areas where the tire slip is negligible. So if we wanted to proceed at higher speeds or like non-dry surfaces in the future, we would need to introduce dynamic modeling of the tire forces. So that's a future work. We could also explore more systematic mechanisms for weight tuning, which would save us a lot of manual tuning time. And then if we wanted to navigate through more dense scenes or scenes where there are dynamic objects in the environment, we would probably want to switch over to a more complex obstacle representation, such as potential fields. Any questions about those future works?
It's really exciting, Rowan. Thanks very much for going through this. And I think it's also really cool how this is really work of our team, right? Over multiple people, over multiple years to bring it to this point. So I think that's pretty exciting to see the kind of cool stuff that we're creating here.
Yeah, thanks very much, Derek. It was great to have Mohammed as a resource, and he definitely helped a lot with this, and is happy to see that it's being carried on into the future. All right, so yeah, thanks very much for your time. I'll post those slides and other resources that I talked about in the All Hands channel. I guess if you're interested in getting involved even further, you can check out the MPC research channel on our WATonomous Discord server, where we're talking about how we can frame this work into a publication.
Awesome. Thank you so much, Rowan. And thanks everybody for coming.
Yeah, actually, just another opportunity came to mind. Charles, maybe you can reach out to the UOFT captain. But I heard from Prof. Fraser, their faculty advisor. I mean, this goes back a few months, so maybe out of date, but they might be looking for some help on, so that the eco-car competition that they are in has been, in the beginning, was all about powertrain, like converting a gas vehicle to a hybrid vehicle. And over time, so eco-car is like in its, fourth or fifth iteration. It's like 15 or 20 years. But it's been adding some connected and autonomous vehicle features. And so they might be looking for a bit of help in that area. And maybe something like our really neat MPC controller here that Rowan's been talking about might be, something that's helpful for them as well.
Yeah, definitely. We should definitely have those conversations. Yeah, thanks everybody for coming. We'll meet again in 2 weeks, I guess. So look forward to talking to you guys soon.
Thanks, Charles. Thanks, everyone.
Looking forward to it. See you later.
Yeah, good work, everybody. Great talk, Rowan.